Yes. What is the purpose of statistics?
Data-driven decisions.
Data-driven decisions. What does that mean?
What to expect?
We want to know what to expect. What does that mean?
If it's less than 5%, then you don't expect it to happen. If it's more than 95%, then you do.
Okay, if something happens less than 5% of the time, then we don't really expect it to happen, or we consider it unusual. If it's more than 95% of the time, then we do expect it to happen, and we're surprised if it doesn't. Okay? So, how do histograms allow us to come up with this information?
They look at the relative frequency.
We look at the relative frequency. And if the relative frequency is less than 5%, then we say that's an indication that it might be an unusual event. And specifically, we would look at the high end or the low end of the distribution to make that happen. However, there's a problem with that, and that is that the histogram is based on just the information that we have in front of us. We don't necessarily know if that's going to be the same in the future. And that's a major problem that we have here because of the process of statistics. What is the process of statistics?
You sample data to understand a population.
I'm using the sample data. I use the sample to understand the population, but samples are always changing. Samples are parts of the population, and so if I do this sample over here, and if it's randomly selected, the next time I do it, I won't get the same results. So my results are constantly changing, and so it's difficult for me to say, well, I know what's going to happen because of this particular sample. The fact is you don't. Really, you can't say that the sample is the same as the population. Later on, we'll talk about more tools that we can use to understand that better. But one of the tools that we can use is the standard deviation. Okay, what does the standard deviation tell me? Now, if you've already answered, I prefer that you not answer. Okay, because I want to share the wealth here in terms of participation, right?
It measures the variation of a data set from.
Okay, the variation of data set from mean. Okay. Now, when we look at that and we say, okay, I have a number, I have a mean, and I have a standard deviation, how can that help me? How can that give me the information that I want? I have it, and it's meaningful, but just the number. If I have this number, how can I know what that's really telling me? And the key to putting all this together then is what we call the empirical rule. And if you have access to your textbook, that's where I want to go right now. I want to go to page 139 in the textbook. This is very important. You need to know this. You need to be able to work with this. This is the empirical rule. The empirical rule gives us the bridge between the data and these numbers and our purpose, which is to know what to expect. This is what happens if we have bell-shaped data. We're able to use the empirical rule. So I put this in capital letters. I'm shouting this in internet speak. If the data is bell-shaped, then the empirical rule is going to apply. Well, we already talked about this. If I look at a data set, how do I know if it's bell-shaped? And the answer is you kind of do and you kind of don't. And as it turns out, many times we just assume the data is bell-shaped and use the mathematical tools, and then if it's not, we're in trouble. So then we have to be careful about our conclusions, because if the data is not bell-shaped, then our conclusions will not be correct. So how does the empirical rule work? It tells us the behavior of the data in terms of the percent for the distribution. How much of the data is going to be in the middle based on our definition of what in the middle actually means. Notice bell-shaped, it has most of the data in the center. And if you look at this thing closely here on the graph, you will see what are the intervals for using the empirical rule. If you look down at the bottom of the graph, you will see a number of symbols. And these symbols that are given to us are the mean with this Greek letter mu and the standard deviation with the Greek letter sigma. So previously we were talking about different kinds of letters, but now we're going to say the population mean is this Greek letter mu, and the population standard deviation is this Greek letter sigma. So by using these letters, we're going to establish how much data is in certain places on the distribution. So when it says within 2 standard deviations, what does that actually mean? When we say within 2 standard deviations, we're talking about having the mean plus 2 times the standard deviation, and having the mean minus 2 times the standard deviation. These are the left and the right sides of an interval. Here we have a number, here we have another number, and then this interval is what the empirical rule is going to be talking about. The most important thing about this, then, for us, is that we can use this 95% rule based on this interval. Let me give you an example. Let's say that people have a mean blood pressure of 120. And let's say the standard deviation of blood pressure is 15. Now, if you remember, how do you figure the standard deviation? It's kind of a complicated formula, and it has a lot of steps in it. But if you have a computer, you just hit a button, and you get the standard deviation. So let's say we have a big data set. We know the mean is 120, and we find the standard deviation is 15. What will that tell us based on this empirical rule? Well, I'm going to take 120 minus 2 times 15. And for whatever reason, people forget the order of operations. We do not subtract first. We multiply. So this is 120 minus 30, which gives me 90. That would be the bottom end of my interval. Well, where's my top end? It's 120 plus 2 times 15. So that'd be 120 plus 30, which is 150. So if this is true, this is the mean, this is the standard deviation, then this will be my interval. So I will say 95% of the data is between 90 and 150. This is the empirical rule for this data set. Unfortunately, students have some trouble with this because I'll ask a question. How does the empirical rule apply to this data set? And they will write down the numbers 90 and 150. That's not it. How does the empirical rule apply to the data set? It is that 95% of the data is expected to be located between 90 and 150. That's the empirical rule. It's not just the two numbers, it's what they tell you about your data. Now, if I ask the question, where would I look for unusual values? The answer to that question would be anything outside of that interval. So when we say, where are my unusual values? I would say less than 90 or more than 150. If I ask the question, where would I expect unusual values for the data? The answer is not 90 and 150. The answer is anything lower than 90 or anything greater than 150. Unusual values would be outside of that interval given by the empirical rule. Now, the empirical rule does not just say what I just told you here. There are also other numbers for 1 standard deviation and for 3 standard deviations. 3 standard deviations is 99.7% of the data. Well, that's basically 100%. So basically, we would say all of the data is expected to be within 3 standard deviations. But the most important idea is this one using 2 standard deviations, because that's telling us what to expect. We don't normally use 3 standard deviations because that would be not according to our standard. We're looking for more than 95%. That's pretty much what we want. So that's why the 2 standard deviations is the important rule. All right, so this is the empirical rule, and this is telling us, in a sense, how to apply the relationship of the mean and the standard deviation. If I know the mean of a data set and the standard deviation of a data set, what does that actually tell me? I use the empirical rule, it will tell me something. However, there is a problem, and that is maybe your data is not bell-shaped. Well, what happens if your data is not bell-shaped? Well, in your textbook, they give you this thing which is not the empirical rule, and it is Chebyshev's inequality. This is beginning on page 140 in the textbook. Chebyshev's inequality says that even if it's not bell-shaped, you can still come up with things that are like what we have for the empirical rule. And so these things are true no matter what the data looks like, a mathematical description of the relationship between the mean and the standard deviation. So then, I don't put this on the quiz, right? Because it's pretty complicated. But there are homework questions having to do with Chebyshev's inequality. The idea of using 1 minus 1 over k squared, which is the number of standard deviations, either to the left or to the right. So then, when we were talking about the empirical rule, this was a 95% using 2 standard deviations. But Chebyshev, we'll just use CH, maybe. Chebyshev would have a 2 in here, which would be 1 minus 1/4, which would be a 75%. So if we're using Chebyshev's inequality, then it doesn't have to be bell-shaped. But now our percentage goes from 95% to 75%. So then we're like, well, that's maybe not quite so useful. It's something though. It's at least telling us something about where we would expect the data to be. So again, it's not something that I'm going to expect you to use, but when you are out there looking at data and it's not bell-shaped, then you can use Chebyshev's inequality to give you some ideas of what's happening. So, in addition to this information that we have, there's another idea that's useful when we talk about the standard deviation, and that is something called the z-score. The z-score will be very important to us in the future, so I'm going to introduce it to you now. What is the z-score? The z-score measures the variation of a specific data value from the mean. So when we're talking about a z-score, it's going to be telling us something about a specific data value. Is it a lot higher than the mean? Is it a lot lower than the mean? Or is it somewhere in the middle? And so then the z-score is actually the number of standard deviations from the mean to the data. I'll give you an example. If we use what we had before for blood pressure, and we say the mean is equal to 120, and the standard deviation is equal to 15. If I were to have a person with a blood pressure value is equal to 165, and I say, what does this tell me about that person? The formula for z-score is the data value minus the mean divided by the standard deviation. So this is how I'm going to find out what the z value is based on the relationship of these numbers. So here it would be 165 minus 120 divided by 15. So this would be 45 over 15, which is 3. So that means a data value of 165 corresponds to a z-score of 3. Well, if you're 3 standard deviations above the mean, then that's pretty high. 2 standard deviations is the possibility of what we said could happen. 3 is like way out there. So that would characterize this as an unusual data value because it's bigger than 2 standard deviations above the mean. Well, what if somebody had a different blood pressure value? Let's say their blood pressure value was 108. What would we say about that person? Well, if we say the z-score is 108 minus 120 divided by 15. What's 108 divided by, or sorry, what's 108 minus 120?
Negative 12.
What's negative 12 divided by 15? Negative 0.8. So if we look at this and we say, well, what about this blood pressure value? It's below the mean, that makes it negative, but it's not very far. It's not even 1 standard deviation below. So we would say, all right, well, I kind of would expect somebody to have a blood pressure of 108. That's not unusual. Where 165 would be unusually high, 108 is not unusually low because it's a z-score of negative 0.8. Now, this is going to be very much important to us later, but I wanted to show you what it means because it does also help give meaning to the relationship of the mean, the standard deviation, and the data values. So if we put all those together, then this is the meaning of the z-score. How far away from the mean is a particular data value in terms of how many standard deviations. In this case, it would be 3 above. In this case, it's not even 1 below. Right? So that should be enough then to carry us through chapter 3 and get you into the homework for next time. Right? So I'm going to go ahead and stop the video